You're all familiar with the Big Bang, the colossal explosion that marked the beginning of time and space. But what if the birth of our universe was even more extraordinary than we've come to believe? Imagine for a moment a universe not birthed from an explosion, but from a white hole. This concept, though purely theoretical and speculative, presents a fascinating twist in our cosmic narrative. This cosmic object is the exact opposite of a black hole. While a black hole is like a cosmic vacuum, swallowing everything in its vicinity, a white hole is a cosmic fountain, spewing out matter and light.
White holes is a solution of Einstein equations, so like black holes, a solution of Einstein equation. So it's a possible happening compatible with Einstein equation, where you have an horizon, but not this horizon where you can only enter. It's an horizon from which you can only come out, and where inside you have this enormous tube, but instead of becoming longer and narrower, it's becoming shorter and opening up. And that's predicted by Einstein equation.
According to general relativity, the gravitational collapse of a massive star leads to the formation of a black hole, a region in space where the gravitational pull is so intense that nothing, not even light, can escape. The boundary of this region is known as the event horizon. White holes emerge from the same equations of general relativity, but with a critical difference. They are essentially time-reversed black holes. Instead of capturing everything that comes near them, they are predicted to expel matter and energy, acting as sources rather than sinks in the cosmic fabric. Rovelli proposes that a black hole could transform into a white hole, provided it meets a key condition. It needs to be exceptionally small. This requirement presents a significant hurdle, as the majority of black holes we observe in the universe are of considerable size, making such a transformation in these cases highly improbable. However, Rovelli adds an interesting dimension to this concept by suggesting the possibility of a quantum jump, adding a new layer of complexity to the theory.
We use quantum gravity to do the calculation. We realized that the probability jumps happen with certain probability. Quantum mechanics about probabilities. Seen from the outside is completely negligible if the black hole is big. It's only possible if the horizon is small. Now this seems to a big problem because, oh my God, but most black holes we see in the sky, they're big. They're not gonna ever happen there. Black holes become smaller with time. Black holes evaporate. They emit energy and they become smaller and smaller and smaller and smaller. So if you wait long enough, even Sagittarius A star, which is this gigantic black hole, even the biggest one, the billion solar masses black hole, are going to shrink and become very small. Once they're small, the probability of jumping is very high. In fact, it becomes order 1 and it jumps. So the correct story, cosmologically or astrophysically, the likely story is that whatever black hole you have, it's going to take some time, at the time was computed by Hawking, to become small, then it jumps, and then becomes a white hole. The white hole is teeny because it's at the end of the evaporation. The inside is big and takes a long time to come out the inside. That's the full story. Now, question is, how long does it take? Well, a black hole, you have to wait for it to become small. And this was computed by Hawking. It's a black hole the size of Sagittarius takes much longer than the life of the universe. So this happens, and there's billions and billions of years. But inside the black hole, we go through these things. Where in the white hole, the time it takes in Sagittarius A star from the moment we cross the horizon, for us, we're inside the starship, we're going down. Again, assuming that we're not squeezed and squashed. Okay, the time it takes for us to go to the jump is minutes for a big black hole. For a small black hole is seconds, even less. The jump is instantaneous, and the time to get out from the white hole is very short, again, minutes. So outside, the time is billions of years. Inside is just seconds and minutes, which means that the full process is something that lasts billions of years for a clock outside, minutes for a clock inside.
The concept of white holes is intriguing, but remains highly theoretical. They have never been observed, and their existence poses significant challenges to our understanding of physics, particularly concerning entropy and the arrow of time. However, this has not stopped theorists from speculating about their role in the cosmos. If Rovelli's ideas were correct, they could go a long way toward potentially resolving black hole paradoxes.
Stephen Hawking initially believed that if you threw information into a black hole, so that, a hard disk or a book or whatever it is, then that information would be destroyed. So it would have disappeared from the universe. And you can see why, because black holes contain the end of time within them. There's this thing, the singularity, which is in a very real sense the end of time. So you throw a book, it goes to singularity, it's gone. But then, of course, Stephen also initiated the study of how black holes radiate. And they have a temperature and they radiate away. And so the question became, well, what happened to that information if the black hole isn't eternal? If it goes, admittedly on very long timescales, it just disappears into radiation and there's nothing left. Then is it the case that the information that you've thrown in is imprinted somehow in that radiation? Or is it the case that it's been destroyed? And for many years, Stephen, actually and others, thought it was destroyed. That's problematic, profoundly problematic, because if you destroy information about the universe, then you can't predict its future. It's called determinism, right? So this idea is central to science, that information is conserved, it's not created or destroyed. And recently, in the last couple of years, I think to most people's satisfaction have solved that problem, at least in a sense that people now agree that information is not destroyed, that it comes out in the radiation. But the actual interpretation of what those mathematical results mean is certainly not agreed upon, because it's bizarre. And so people are talking about wormholes connecting the interior of the black hole to the far distant Hawking radiation that was emitted, billions and hundreds of billions of years ago. People talk about something called the holographic principle, which is the idea that really it comes from the observation that the information seems to be in some sense stored on the black hole's surface, on the surface of the event horizon, and not in the interior. And in some sense, the interior doesn't seem to exist, certainly in some pictures. So all this tremendously advanced work on black holes and the information paradox has come about in the last few years.
This principle, while primarily concerning black holes, opens up intriguing possibilities when we consider the birth of our universe. If the information in a black hole is preserved and encoded in this way, could a similar process be involved in the emergence of our universe from a white hole? This line of thinking suggests that the origin of our universe might not be a simple point of singularity. Rovelli's theories about black holes and white holes, coupled with insights from the information paradox and the holographic principle, offer a new lens through which we might view the birth and evolution of the universe. It's important to note that while Rovelli's ideas are grounded in theoretical physics and have generated significant interest, they remain speculative and are a subject of ongoing research and debate.
The first evidence, the first time astronomers could see something in the star and they thought, well, that's maybe a black hole, was in the 70s, but it was just a few astronomers, nobody was taking them seriously. There were some stars that were wiggling. We could see the Doppler effect, they're moving back and forth, like if we're rotating around something, but there was nothing around which to rotate. And somebody says, maybe it's a double star, and one of the two is a black hole. It's only really this century that people, the scientific community at large, started taking the idea that black holes are real seriously. So why I'm saying all this? Because in the 30s, this guy constructed this antenna, and he picked up a signal from a point in the sky which was in the center of the Sagittarius constellation, and it was called at the time Sagittarius A star. He was seeing the black hole. The signal, the radio signal of the black hole, was received for the first time on Earth by somebody in the 30s. It took half a century to recognize that that was a black hole. So it is not totally impossible that white holes is something we have already seen. We know quantum mechanics, we know general relativity, we know what happens to a black hole up to there, and you keep turning things around until you find the little hole that allows you to put together a puzzle in a different manner, in such a way that makes sense, and there's a possible step ahead. And then, experiment tell you whether it's right or wrong.
As we delve into these cosmic possibilities, the idea of white holes challenges us to rethink everything we know about the universe. It's a thrilling reminder of how much remains unknown, sparking our imagination and pushing the boundaries of science. This pursuit, driven by a mix of wonder and rigorous inquiry, is what keeps our quest for understanding the universe so alive and exciting. Whether or not white holes exist, they symbolize our relentless drive to explore the unknown and unravel the mysteries of our spectacular cosmos.